Hey there, welcome back to A Slice of Physics. In this session, we're going to look at uniform circular motion. That means going in a circle at a constant speed. We're going to first take a step back and look at velocity and acceleration vectors and see how they are related to each other. And then we will apply what we learned with that to the uniform circular motion to figure out what is the acceleration involved in uniform circular motion. Let's take the example when I'm driving my car around a perfectly circular track. So here's the circular track as it looks when I'm viewing it from above. And here's my car. And I'm driving this car at a constant speed v around this track. So the car's on cruise control, and that's what tells us that this is uniform circular motion. The word uniform in circular motion simply means constant speed. So let me ask you a question right off the bat here. Is there an acceleration involved in uniform circular motion? A lot of you might be tempted to say that there is no acceleration involved because we have a constant speed. We're on cruise control. But that answer is wrong. There is acceleration involved because you remember that acceleration is related to change in velocity. And even though the speed's not changing, the velocity is changing because velocity is made up of speed and direction. And in this motion, I've got the direction changing constantly as I'm turning around the circle. And so the velocity is changing, and whenever I have a change in velocity, I have acceleration. So our goal is to understand that acceleration and see what it is, which way it points, and what its magnitude is. Now, before we do that, let me just take a step back and look at the relationship between velocity and acceleration vectors based on some of the things we have learned with a straight line motion. So I've got a straight road over here, and I'm in my car over here, and I'm moving to the right, and the traffic clears up, so I get a chance to push on my gas pedal and go faster. So as I do that, my velocity vectors go from a smaller arrow to the right to a larger arrow to the right. So let me label this VI and this VF. So what is the acceleration here? We have discussed this in the past conceptually, but now let's look at it through vectors and see if we can make sense out of the direction of acceleration here. We know that acceleration is nothing but change in velocity over change in time. And because change in time is a positive scalar, the direction of acceleration is always same as the direction of change in velocity. We've discussed that before. And the change in velocity is simply the final velocity minus the initial velocity. And now that we know how to do vector addition and subtraction, let's see what that turns out to be. So to subtract VI from VF, I have to start with VF over here. I have to reverse VI because the minus 1 times VI simply switches direction, does not change the magnitude. And then I slide that over to the tip of VF. So here's my minus VI. And when I add those two vectors, my resultant acceleration vector points like that. So that just matches what we know from before, that when I'm speeding up, the direction of acceleration is the same as the direction of velocity. Let's also look at what happens when I slow down. So I'm back here in my car, and now I see a lot of cars piled up ahead of me, and so I slam on the brake. So now I'm slowing down. As I slow down, my velocity goes from a larger value initially to a smaller value as a final state. And so when I do the vector subtraction, my VF minus VI, VF is over here, minus VI is over here. And when I add those two, I will get the net acceleration vector as something that's pointing to the left. The direction of acceleration will be opposite the direction of velocities when I am slowing down. Okay, so hopefully this was a review of some of the concepts we've been discussing already, but we looked at it more formally through working with vectors. Now, one more thing before we go back to circular motion. What do you feel as you are speeding up and as you're slowing down? From experience, as you speed up and push your gas pedal to the floor, you feel pushed back into the seat. And as you slam on your brake, you feel like you're going to fly out through your windshield. Now compare the direction of what you feel to the direction of acceleration. So if I were to show what you feel pushed back, that's opposite the direction of acceleration. And here you feel like you're going to fly out of the windshield this way, and that's again opposite the acceleration. So this is a key point here. What we feel is always opposite the direction of acceleration. And why is that? Because of inertia. That's the property of matter that we will be discussing in the next video that tends to maintain its state of motion. We don't like to change things. And because we want to resist that change, we feel like we're being pushed back into the seat when the car is speeding up, and we feel like we're going to fly out of the windshield when the car is slowing down. That's useful to remember as we go back to circular motion. So back to circular motion, I've drawn a bigger circle here to see what happens to velocity at a few key points along the circle. So let's say my car is over here, and I want to find out the direction of acceleration while I'm making the turn. So to do that, I need the initial and final velocities. So let me take the velocity at this point before my point of interest and this point after my point of interest, and draw some velocity vectors. You remember that the direction of velocity is always tangent to the curve in the direction of motion. So my direction of motion is like this, clockwise around this loop. So my initial velocity will be tangent and point like this. My final velocity will have the same length of the arrow, but now the tangent to the curve at this point looks like this. And when I take that VI and VF and move them to my point of interest, my VF is over here, minus VI looks like this over here. So this is VF minus VI. And so that gives me an acceleration vector that in this case points straight down. Let me take a point over here and see what happens. So now my initial velocity points like that. My final velocity points like this. And to subtract VI from VF, I flip VI, move its tail to the tip of VF. And so that's something like that. And so my acceleration vector will point in this direction. And let me just move it to my point of interest and show it over here. What's common between these two things? Here I'm pointing straight down, and here I'm pointing to the left and top. But you see that both of those are pointing towards the center of the circle. And for practice, you can take other points along the circle and do the same exercise, and you will see that no matter where you are, you're pointing towards the center of the circle. So when you are in uniform circular motion, your acceleration always points towards the center of the circle. And it's got a name that captures that property. It's called centripetal acceleration, meaning it points towards the center. Now, all this may be a little bit surprising to you, so let me put it in context like this so it makes more sense. We discussed in the past that if my velocity vector points to the right and my acceleration vector also points to the right, you would be speeding up. So your final velocity will be bigger than your initial velocity. And if your velocity vector is pointing right, but your acceleration vector points left, the object would slow down. So final velocity would be smaller than initial velocity. So what do you think might happen if I've got a velocity vector that points this way and an acceleration vector that points that way? Because this is kind of supporting the velocity, you might say that the final speed would be faster than the initial speed, but because the acceleration is kind of nudging it in that direction, the final velocity might point something like this. And that would be correct. You can do VF minus VI and see that you would get the right direction for acceleration from this. And lastly, if I have the initial velocity pointing like this, and I have an acceleration vector that points that way, you would expect the final speed to be smaller than the initial speed because the acceleration is opposing the velocity, but it's also turning it downward. So it might look like this. And once again, you can do the vector subtraction to verify that for yourself. So that brings us to our circular motion again. What do you think might happen if I have an initial velocity that points to the right and an acceleration vector that points perpendicular to it straight down? Well, this is when, because the acceleration vector is neither supporting the velocity nor opposing it, it's not going to speed up or slow down. It's simply going to change direction. So the final velocity would look like that. It would turn with no change in speed. So the length of these two arrows is the same. That is our uniform circular motion case, where the velocity vector is always perpendicular to the acceleration vector. And that relates back to what we discussed here. The velocity vector is always tangent to the curve. The acceleration vector perpendicular to the tangent will always be the radial vector or pointing towards the center. So we've seen that by taking vector addition at a few points. We've discussed it conceptually here, and it all ties together nicely. The final point for us to discuss with uniform circular motion is what's the magnitude of that acceleration. I'm not going to show you the derivation for it, but the magnitude of the acceleration turns out to be the square of the speed divided by the radius of the circle that I'm turning around. So in this case, this would be r, the radius of the circle, and v is the speed. So this is the magnitude of acceleration, and the direction is towards center of the circle. So given that I've specified magnitude and direction, this is a full vector definition of centripetal acceleration. So what this tells us is that if I go faster around a turn, my acceleration will be a lot higher. Because of that squared term, you're going to have a bigger impact. So doubling the speed will quadruple your acceleration. And if I go around a smaller circle with a smaller radius, if I turn sharper, my acceleration will also be higher. We know that from intuition. The faster you go around a turn, the more you feel like you want to resist the change, which means the change is bigger. And the sharper turn you make, the more you feel thrown out of the center of this circle, which also tells us that the magnitude of change or acceleration is higher. So in this slice of physics, we learned more about velocity and acceleration vectors. We did some vector subtraction to see how acceleration is related to change in velocity. And we also saw that when acceleration is perpendicular to the velocity, the speed does not change, but the direction changes. And that's what happens in a uniform circular motion. Thanks for watching.